spectrum you can plot for a time scale. So when you will plot for time history record, that means for single time history. When you are plotting single ground motion, you can plot SA versus T or SB versus T or SD versus T or SA versus F or SA versus omega. Okay, all are same. So you will get a curve. This curve will be somewhat changing. So this is response spectrum of a ground motion. But when you are designing, our problem in designing which ground motion I should design for, because I do not know that ground motion which is going to occur at the site. Okay, and whichever ground motions have been recorded in the past, none of those will be repeated. The one which I am going to get at my site will be different from all of those. So what should I do? So I need to consider a number of ground motions. Okay, one single ground motion is not adequate. So what we do some statistical operations. So statistical operations on ground motions are complex, are not easy. Okay, because if you take a number of ground motions, suppose I have one ground motion here, UG double dot with T, another ground motion, and I try to take average. What will I get? If I take a number of ground motions, it will become almost zero, isn't it? Some will be having peak here, some will be here, so I can't do those statistical operations here. But I can do those statistical operations very easily here. So if I have a response spectrum here, another response spectrum here, I can take average of those. So these statistical operations are done on response spectrum. That's why those attenuation relationships which we are talking, those are also in terms of response spectrum. So what we do, we consider a large number of such response spectra and we develop what we call a smoothened response spectrum. So a smoothened response spectrum is obtained by averaging a large number of normalized response spectra. Okay, so when I take a large number of response spectra which are normalized with respect to the EPGA, I will get some average shape. This is the smoothened response spectrum. Okay. Now, in design, what I do, it is having a peak. Okay, so there will be always uncertainty that here where the peak should be, the peak period can differ. So in design, what we do, we do design response spectrum. So as I have explained in the tripartite graph, we identify three ranges: the acceleration control range, velocity control range, and displacement control range. So this smoothened spectrum, which I have got from a number of earthquakes, considering a number of earthquakes, I further idealize it like this. This is our design response. So we divide it into three different segments or ranges of period: the acceleration control range, velocity control range, and displacement control range. And I fit very simple relationships here. Here it is constant. Here it is some CV over T. Here it is CD over TC. So I fit simple relationship in these three segments. This response spectrum is used in all design codes. Okay. Till now, all the design codes have been using this. Our code is still approaching in that direction. You have seen in IS 1893-2016, we don't have this displacement control range. Rather, beyond this, it takes constant. Okay. But if you look at Eurocode and American code, their response spectrum has these three segments. Okay. Now American code has gone one step further. Now they are trying to take the smoothened spectrum. So they have two alternatives now. Either you can use smoothened spectrum because they have lot of confidence now that where this peak will occur. Okay. Because there is uncertainty in this peak, so they consider this as flat. But now they understand that where the peak is occurring, so they are going one step further. So recently revised AC7, AC722, they have introduced the smoothened spectrum also, smooth spectrum also. Okay. There is another nomenclature for this, what we call uniform hazard spectrum. What is that uniform hazard spectrum? I will talk slightly later when I will talk about PSC. Uniform hazard spectrum. So this smoothened spectrum, this is also called uniform hazard spectrum. So they have started using uniform hazard spectrum because initially not many ground motions were known. Okay, we started recording ground motions in 60s only, and Newmark, I think somewhere around 80s, he gave this concept. So when nothing was known how to define this response spectrum, so they have given a simple shape. Their CA is some factor times alpha v, some factors times PGA. CV is obtained from PGV and CD is obtained from PGD. Okay, so this spectrum was easier to define, and that's why in most of the codes the response spectrum which was given in our code was not based on really measurements, it was more based on judgment. So code committee, the people they decided that okay, in this zone we will use this, in this zone we will use that. Okay, but in US now they have lot of data, they have lot of confidence about shape of this, they have done some exercises. So they have now gone one step forward and they are using this uniform hazard spectrum or smoothened response spectrum directly. So that alternative they are taking. Okay.
So rather than going for smoothened, why we are not taking the backbone of all these spectrum?
Backbone you mean envelope?
Because if we take the envelope now, all this spectral accession will be counted.
See, the problem with envelope is always that the maximum and minimum is never known statistically. So what you can know is you can know mean or median and median plus sigma or median minus sigma. So generally these are different. Okay. So I have shown you this average, but actually we do not take average. We take, I will tell you later that we actually take mean plus sigma. Okay. So we never take envelopes because envelopes can always be, envelopes are not defined. Okay, in statistics, envelopes are never defined. 0 or 100% probability is never defined. Okay, but what you can define is a given percentile or given probability. So 50% mean plus sigma corresponds to 84%. Okay, and so on. So those are defined. Those we will use. So we will be using, actually we will be using mean plus sigma. Okay, clear? So let's move forward.
Sir,
yes.
हमने response vector को 3 सेशन में डिवाइड किया है, acceleration, displacement, development. Right. तो displacement control और acceleration, what does it mean? It controls.
Controls means I explained yesterday also that the value here, the value of spectral acceleration here is controlled by peak ground acceleration. The CA is some factor alpha A times PGA. I have explained yesterday. So this value is controlled by acceleration of the ground motion. That's why we call it acceleration control range. Here the value is controlled by the velocity
of the ground
motion, and here the value is controlled by the displacement
of the ground.
Okay. Why this? Why here it is controlled by acceleration and here it is controlled by displacement? That you can understand with a simple logic. I have already discussed short period means what? Rigid. Okay. So a rigid structure, a block will give you simply EPGA. If you have a rigid structure, let us say shear wall, a structure which is very rigid. Okay. What will happen? The acceleration will not be same, okay, but it will be somewhere, some multiple times this. Okay. On the other hand, think of a very flexible structure. Very flexible structure. So what will happen? When the ground is moving, the mass will remain in its own position. Only the ground will move. When it is going in the other direction, the ground is moving. Okay. But the mass, if it is very flexible, what will happen? The mass will try to remain in its position. Due to inertia, the ground will move. So how much is the relative displacement? We are measuring the relative displacement. So this relative displacement, that is equal to PGT. But that will happen when it is very flexible. Okay. In between, what will happen? It will be controlled by velocity. So response of a rigid system will be controlled by the acceleration of the ground. Here it will be controlled by UG. So maximum response will be equal to UG max, the relative displacement. So ground displacement itself will become the relative displacement. And I told you yesterday that the SD, okay, is actually the relative displacement, not the absolute displacement. This is the relative displacement. Okay. So rigid structure, behavior will be governed by acceleration. Flexible structure, the behavior will be governed by displacement. Intermediate range, it will be governed by velocity. And we have seen that by plotting on tripartite graph. So any response spectrum for any ground motion, if you plot on tripartite graph, the shape goes like this. So here it is governed, it is parallel to, or it is, it is parallel to a constant acceleration line. Here it is parallel to a constant velocity line, and here it is parallel to a constant displacement. Any other doubt?
Yes.
Yes.
So when the ground is shaking, the static center is going to go into low state, and then travel to the ground. Means go upper soil level. So the wave propagation level from higher medium to the lower level. That means the wave reflects from its position, and that's why it is not directly to the structure. Some path.
Anywhere the wave, the wave will start from the fault where the rupture has occurred. This elastic wave will travel. Whatever medium will come, it will never be a homogeneous, uniform medium. There will be always interfaces. Okay. So wherever an interface will be there, wherever there is a change in the medium, there will be reflection and refraction. Okay. This reflection and refraction is also responsible for attenuation. Yesterday I talked about damping. So damping is just one way of dissipating energy. Another is this reflection and refraction. So the wave, part of the energy gets reflected back and part of it gets transmitted. This happens at every interface. Whether that interface is within the rock, it is rock versus soil, or it is different layers of soil. The maximum change in the characteristics takes place at the interface from rock to soil, because there is the change in the properties, what we call impedance. So the impedance contrast is maximum. So when the impedance contrast is large, that means the velocity in one medium and the velocity in the other medium is very much different. Okay, then maximum reflection will happen. Okay, so this happens. So it is at every interface. It is not occurring only any one interface. On all interfaces, this happens.
Sir, another meaning of this is like this: if my structure is very rigid, then force will come on this. Then I will check my capacity of the structure. If my capacity is greater than this force, then my design will be okay. When I am going to flexible structure, I will check for the displacement. That displacement causing from this response spectrum of my structure, that should be less than my principal displacement. Then my design will be okay. This for the rigid structure.
What you are saying is that provided here and here you are assuming the structure to remain elastic. So what you are saying for elastic structure, it is okay. So if you are designing your structure for force larger than this, then the structure will remain elastic. But the complication arises further because we never design elastic structures.
Yes.
The structures are inelastic. So in case of inelastic structure, we never design for a strength larger than the force which will be caused by the earthquake. We design for lower strength. Okay. And then there is a problem. Then what you are saying is not valid. Okay. So finally, whether it is here or here, the design is governed by displacement only. Because failure will not depend on force. Failure will depend on
displacement.
Okay. So when the ultimate displacement is reached, then failure will occur. If the yield force is exceeded, failure is not occurring. Even the ultimate force is being exceeded, it is not failing. Failure will occur when the yield displacement. Okay. So force is not the proper criteria for appropriate criteria for deciding the safety of the structure. It is the displacement. Okay. So let's go for steps in deterministic seismic hazard classification, DSH. So the first step in DSH will be identify and characterize all the sources in the vicinity of site. We discussed what is meant by vicinity. Within a radius of 300 kilometers. Okay, and 300 kilometers is not a very large distance when we are talking about earthquake. Yesterday we have seen that if a magnitude 9 earthquake, we calculate roughly the fracture length, that is about 1000 kilometers. 8 magnitude earthquake itself has about 200 kilometers fracture. Okay, so if you look at the seismotectonic atlas, there are very long fault lines within the country in the northern part, which starting from western Himalaya, going this whole Himalayan range, it covers. So 300 kilometers is really vicinity when we talk in terms of earthquake. And another word I have used, characterize. What is meant by characterize? Type of fault. So is that enough to characterize the fault? The most important is magnitude, potential. Okay, how much magnitude earthquake it can cause. So magnitude, then the type of the fault, because same magnitude yesterday you have seen, no, not yesterday, we will see it today. Same magnitude earthquake, if it is having different fault mechanism, that means normal, reverse, strike slip, okay, it may cause different intensity of the ground. Okay, so all those characteristics are needed. So that is the characterization. Then we develop we calculate intensity of shaking at site, considering the sources characterized above. Step 1, and distance. For this purpose, we will need attenuation relationships or predictive relationships. I will talk about these relationships today. Okay, so I can calculate intensity. What is meant by intensity? If I say I am calculating intensity, then what actually I am calculating intensity? I can calculate PGA, I can calculate PGB, I can calculate PGD, or I can calculate response spectrum itself. All these are measures of intensity. So any of these or all of these I can calculate. Then I will calculate or I will identify the governing earthquake causing maximum intensity. Okay, so that source which is giving maximum intensity at my site, that condition I will double, and then I will generate design responses. Okay, so these are the different steps which we have to follow. Now, step 1 we have discussed yesterday, how to calculate magnitude corresponding to a fault. One way is looking at the length, area or displacement if that information is known. The other way is estimating the magnitude of all the past earthquakes which have occurred. So based on that also I can predict that what is the potential, what maximum earthquake can be generated. Okay. The only problem is that the data for past earthquakes which we have is only for 50, 60 years, 70 years. Okay. So based on 70 years, we are predicting much longer periods. We will talk about those periods. We are talking like something like 4,500 years or 475, 2,500 years. Sorry, 475 years or 2,500 years. Okay. So that large period we are trying to predict, and that's the source of error. That is the source of uncertainty. Okay. So second step I want to talk today, that is attenuation relationship. These attenuation relationships are developed based on past earthquake records. Okay. So when we are talking about past earthquake records, then there is a possibility or the applicability of these attenuation relationships will depend upon which earthquake data I have considered. Okay. So I will give you two typical examples. One is Campbell in 1981. Okay. And you can imagine in 1981, the measurement started in 60s. Very few records were available. Okay. So they considered worldwide data. Based on whatever data was available, they used that. Okay, and the relationship they developed was log of PHA in the units of G, and natural log. Okay. In some of the relationships you can see they have used natural log, and some of the relationships they have used log to the base 10. And the relationship they got was minus 4.141 plus 0.868 mm. Okay, minus 1.09 log R plus 0.0606 e to the power 0.7. This is one of the simplest relationships. Okay, because lesser data was available, so they considered worldwide data, whatever was available, and here M is magnitude of the earthquake. And I told you that when you are considering magnitude, it is very important we should know that which magnitude has been used. So at that time, they considered the Richter or local magnitude. If m was greater than 6, okay, and surface wave magnitude if m was greater than 6. And R is the closest distance from the fault to the site. So closest distance. And when you are fitting an equation, there will be always some variability. All the data is not going to fit perfectly. Okay, so there will be some variability, and that variability we can represent by standard deviation. So they also calculated the standard deviation in log of PHA is equal to 0.37. I will tell you later what is the utility of this. This value of sigma will be used. Okay, so if you know magnitude, if you know distance, you can calculate. Now look at our tutorial number 4, question number 6. So different sources, faults are given. Some of the sources are line sources, some of the sources are area sources. So what you have to do, depending on the size, length or area of the fault, okay, you can assign a magnitude. You can obtain a magnitude using Wells and Copper-Smith relationship. Okay, so that will give you the magnitude. Then coordinates are given, so you can calculate the shortest distance. Okay, and then you can calculate using this relationship. You can calculate PHA. What is PHA? Peak horizontal acceleration. This is nothing but EPGA. So that EPGA you can calculate for each of these sources which are given. Then you can determine the peak value of EPGA which you are getting due to any of these sources. These different sources having different magnitude and different distances will give different values of PHA. You will take the largest value of PHA, and then for that you can develop the response. Okay. There, in that relationship, in that question, the type of the fault is also given. Here in this relationship, type of fault is not appearing because at that time they considered all the faults. Okay, that much information was not available. But later on, so many relationships got developed, and one relationship which we are using, it was developed in 1993. This is also now sort of obsolete. Much more sophisticated relationships are not available, are now available. Okay, so Bohr in 1993, what he did, that rather than considering the world over data, because world over data it was occurring in different types of sources, okay, different path characteristics, so it was not justified to put all the data together. So the attenuation relationship should be region specific. What relationship I am developing for US, that may not be valid for India. What we are doing for China, okay, because that is other side of the Himalaya, may not be valid on the lower part, okay, in the Indian side. So what they consider North American data. And the magnitude they were having, they got was from 5.5 to 7.7. This magnitude they got. And the distance for which the records were available or they used was 100 kilometers. So we have to keep in mind that this attenuation relationship will be valid only in this range. Okay. Distance less than 100 kilometers, you can't use it beyond 100 kilometers because that was not used while developing the relationship. Okay. And this distance was measured from surface projection. Of the fault. Actually, fault is inclined. You project it on the ground surface. From projection, you take the closest distance. That will give you. And the type of the magnitude they considered was moment magnitude. Okay. And the relationship which they have obtained is log. This is 2 to the base 10. PHA in the units of G is equal to B1 plus B2 plus MW minus 6 plus B3 MW minus 6 square plus B4 R plus B5 log of R plus B6 GB plus B7 G. Okay. And here R is actually square root of D square plus H square. This D square, sorry, D is the horizontal distance which I have given here, distance. So D is horizontal distance from surface projection of fault and H is a parameter representing depth of focus or hypofocus. I told you yesterday you can take horizontal distance, you can take from the epicenter. Okay, so H is a representative of the depth. Okay, and then they developed tables to obtain this B1, B2, B3, etc. Before that, this GB, here a parameter GB is used. GB and GC. Is GB and GC? These are representing local site conditions. Okay, so ground motions, do not depend only on magnitude and distance. Okay, those also depend on what type of soil, what type of strata is there on which the instrument is put. Okay, so first time they considered that, and this GB depends on GB and GC. These are representing site class. Okay, and site classification depends on VS30. Anybody knows what is VS30? Shear wave velocity at 30 meter depth. What is VS30? अनिरुद्ध, जियोटेक्निकल का इज्जत का सवाल. What is VS30? Average shear wave velocity in top 30 meters of soil strata. Okay. How it is obtained? So this VS okay, so VS is the square root G by rho. Okay, shear wave velocity depends on shear modulus and density. Okay, so this is square root G by rho, and it will be different for different layers. Let us say this is D1, this is D2, this is D3, and so on. So you take weighted average of that will give you VS30. Okay, so if you are calculating velocity, so it will be 30 meter divided by the time taken to cover 30 meter. How much time will be taken to cover 30 meter depth? In first case it will be D1 over VS1. In second case it will be D2 over VS2 plus so on. Okay, up to 30 meter. So that this summation of D is equal to 30. So you take D1 over D over Vs for each layer till a depth of 30 meter. Okay, then 30 divided by that will give you the Vs. How it is measured? You can, if you know the value of G, you can get shear wave velocity. But do you know any test method by which we can obtain any test you have heard which can be used to obtain shear wave velocity? The most reliable test is a cross borehole test. So in cross borehole test, what we do? We make 2 or 3 boreholes at some distance, and we put one instrument in one borehole, another instrument in the another borehole. One is the transducer of shear waves, another is the receiver. So at different depths, we take these transducer and receiver at different depths, transmit shear waves, receive at the other cross borehole, and by taking the time difference and the distance, we can get the shear wave velocity. Okay, so that is most accurate method. And another one is what we call MASW. Okay, multi channel analysis of surface waves. Okay, so MASW. Both these equipment are there in our lab, geotechnical. Okay, so you may go, and at least geotechnical people should know. Maybe you can use that also. So that is the way it is obtained. Okay. Do you know what is the commonly used test method for soil in industry? Both these cross borehole and MSW are costly, but one test generally we do. Which test? most commonly done? Cyclic? Plate load test. So cyclic, what cyclic? Cyclic what? Cyclic only means cycles of what? Cyclic triaxial you mean? Cyclic triaxial is even more complex. Okay. So you have to remove the sample and then you have to put in cyclic triaxial machine. That is also there in our geotechnical lab. You should go and see. So most commonly used test is SPT, standard penetration test. Have you seen that?
Yes.
Even if you are a structural engineer, you should know what is SPT and how it is done. Simply we drop a weight and see how much it is penetrated. Okay. And what we get is N value. Commonly we call it N value. Okay. So that is always done. You will see whatever investigation, whatever building or bridge you are designing, most of the times in geotechnical investigation you will get N value. Okay. So that results are generally available. Shear wave velocities are not generally available until unless it is an important project where you are spending more money on investigation where cross-bore work is done. So if it is a major bridge, let us say cable stayed bridge, then perhaps they will go for cross-bore work test. But most of normal structures, they will go for SPT only. So there is another possibility that there are empirical relationships, number of empirical relationships between Vs and N, SPT value. Okay, so we will use this relationship. Just check in that tutorial, the back side, have I given you some relationship? I have given only the layers. I think I have not given the relationship. We will give you. Okay. So there are number of relationships. One we will give you, which you can use. Okay. To calculate shear wave velocity. So if shear wave velocity test is done directly, you can calculate VS30 like this. If shear wave test is results are not available, you have only SPT values, then N value you will convert into shear wave of each layer and then you can calculate VS30 like this.
Sir?
Yes.
This SPT number that we calculate on test, that is used for calculating the same bearing capacity or bearing capacity.
Yes. It is actually done for calculating bearing capacity, but we can also use it to calculate shear wave velocity.
But there is no correlation between velocity and that applying force. Shear velocity.
There is. That's how they have developed. But that relationship, correlation is not very strong. And that is the reason there are so many relationships. Okay. So everybody has taken some data and tried to get a relationship. Then somebody has taken another data set and he has tried to develop another relationship. And both relationships are different. So if that velocity and N value relationship was, correlation was strong, if there was a strong relationship, they would have got the same relationships. Okay. This correlation is not strong, but it is workable relationship. They can relate reasonably Vs value with N.
Whatever they are relating, that should be on basic principle of like energy or something, relative difference of like this. Here in cross boring we are making the time with traveling of wave,
Right.
and calculating time with difference. How
Right.
we are relating to that one.
So let's think it this way. On what properties shear wave velocity will depend?
Shear wave velocity.
Suppose it is a sandy spot. So what do you think? On what value the shear wave velocity will depend?
And the resistance provided by that sand while traveling there and the
Right.
voids in that sands.
Right. So on what properties of this is how you are defining
Yes.
the shear wave velocity. What properties of sand? Like properties of sand may be density, C, phi.
Angle of it, yes.
So on what properties it will depend? It will depend on density.
Yes.
Okay. How much compaction
Yes.
has taken place, that is represented by the density, and the phi value.
Yes.
Basically it will depend on these parameters.
Yes.
On what values N will depend?
Bearing will depend
or your bearing capacity, which you are trying to determine,
how much soil is compacted
and
shear
5
resistance.
mm, 5 mm,
Yes, 5
shear
mm.
resistance.
Yes.
Okay, so both are depending on the same parameters, so those are related. So it's not that those are not related, those are related, but the relationship, the correlation between them is not very strong. Okay, that's the reason that different people have come out with different relationships. Okay, so large number of relationships are yes, and that is the problem, that which relationship you should use. Okay, so ideal thing will be that you develop a relationship for in situ conditions. Suppose you are working on a large project, so you make few cross boreholes, develop a relationship between n value and shear wave velocity yourself, and then use those for the other applications. Okay, that is the ideal situation. But if you could do cross borehole, then there would not have been much problem. People don't want to do cross borehole because that is costly. So the SPT is much easier, much cheaper. So that's why most of the times you will get only n value. So in that case, n value you have to convert into VS and then to VS30. Okay, so the site class is based on VS30. So site class, they define, would classify, consider three classes: A, B and C, and the corresponding VS30 they took was A, it was rock, where the shear wave velocity is greater than 750 meter per second, n value greater than 50. Okay, that is site class A. Then B, they considered their VS30 value 360 to 750 meter per second. Okay, and C 180 to 360. Now there are even more classes. You can have less than 180 also. Okay, but these are the three major classes which they considered, and the parameter GB and GC GB is 0 for site class A, it is 1 for site class B, and it is 0 for site class C. Okay. Similarly, the factor GC that is 0 for site class A, it is 0 for site class B, and it is 1 for site class C. What does that mean? In this attenuation relationship, for site class B, this parameter will come into picture. For site class C, this parameter will come into picture. In site class A, both of these will be changed. Okay? And then by performing regression on this data, they came out with the values of these coefficients. Okay, so B1, B2, B3, B4, B5, B6, B7. Okay, and also parameter H and sigma log H. The standard deviation, which is giving the goodness of fit, how this was fit, what was the variability there. And they did two exercises. One, considering random components of earthquake. So they considered random component of earthquake and larger component of earthquake. What is meant by random and larger? So any earthquake, if you measure, you will measure two components, two horizontal components. Okay, out of that, one will be larger, another will be lower. Okay, so if you consider only the larger component of all the, then you will get these values. If you do not consider larger, you consider all, okay, it will become random. So it may be larger, it may be smaller, that is random. If you consider only larger component, you will get these values. So B1 is minus 0.105 and minus 0.038. B2 0. No, sorry, not B3. B2 is 0.229 and 0.216. All this I have taken from Kramer's book. So you can find these relationships in Kramer's book also. So B3 and B4 both are 0. B5 minus 0.778 and minus 0.777. B6 0.162, 0.158 and B7 0.251 and 0.254. You can see slight difference in these. H is 5.57, 5.48, okay, and sigma 0.230 and 0.280. So with the help of these coefficients and the relationship given, okay, you can calculate PGA. When it is 0, 0, why these have been put there? Okay. So in these relationships are semi-empirical. So what they did? First they identified that what should be the governing parameters physically. Okay. So for this particular data set, it may come out to 0. But there may be other data set. So first they fix the form of the equation. Regression, and you have seen how complex these regression relationships are. So first they decided the form of the equation, and then they obtained the coefficients. So for this particular data set which they used, these came out to be 0. But suppose you are doing it for India, these may not come out to be 0. So first they decided the form, and then they calculated the coefficient. Okay. And we will see later for some other same relationship in some other context, then I will show you. Okay. So with this, can you calculate PGA? For that tutorial question? Or you need any other information? I think all the information is with you.
When to consider, sir, a random and larger component?
Okay. So it depends on your objective, whether you are developing for all the components of earthquake considering, or you are considering for a, if you know the direction, then the larger component. To be on safer side, use larger. So if you know that the component which will be coinciding with the direction of your building is larger, use larger. If you are not sure, okay, use random, which considers both. Okay, so can you do that? Now you can determine which earthquake is giving the largest PG. That is your governing earthquake. And then can you develop the design response spectrum once you know the PG? How you will obtain the design response? Once PGA is known, how to develop the design response spectrum? I explained just now. What you need? You need a spectral shape. That spectral shape you have to multiply by the CPJ. So where is the spectral shape? Code. So what is given in code SA by G versus T is nothing but spectral shape. You take that SA by G in the code, multiply it by EPGA, that will give you the response. Okay. Now, Moore have also given this relationship for developing the full response spectrum. SA versus T directly by giving B1, B2, B3, B4, B5, B6, 7 for different values of T. So on. Okay. How? In
Where will I get my program?
नहीं अच्छा was not that. होम से जाना होगा Okay, so Boer has given this table. 0.1 period, 0.11 second period, 0.12 second period, and for each of these period, B1, B2, B3, B4, sigma, all parameters are given. So you will apply the same relationship, but coefficient you will use from here. And then what you are going to get? 5% then PSV, not PGA. This is 5% PSV. What is PSV? P, spectral velocity, pseudo velocity. So what it is giving is pseudo velocity. We want to plot spectral acceleration, acceleration spectrum. How we will get? This you will multiply by omega, okay, or 2 pi by t. So using this relationship, you can calculate the spectral velocity at different periods. Plot those, you will get velocity spectrum, convert that into acceleration spectrum. So you will get the complete shape, okay, and you can plot the full response. This is our DSH, deterministic seismic hazard assessment. Okay. When we meet tomorrow at 4 o'clock. अच्छा कल फ्राइडे है, फ्राइडे में हमारी क्लास नहीं मिल लेते हैं, अच्छा लग रहा है। Okay, then we will meet on Monday. Then I will tell you what is the difference between DSHA and PSHA. PSHA will not be, we will not be doing, but I will give you what is the difference between PSHA and PSHA. If